One is just to introduce me as a speaker, and many of you know that my degree is in nuclear physics. I have a doctorate from that from many years ago. But now I've worked in the high-tech industry for the last 45 years, and I've also done a lot of apologetics teaching here and overseas, different Bible schools and churches. And I try to show people where the Bible and science, they really do agree with each other. You don't have to worry about that. So a lot of my teaching is done on that. So I'm going to get right into it. Let me bring up this slide here. I've got a slide here, which a PowerPoint slide. Okay. And I show a number of people on here. Some of you will recognize the names here. On the left side is some people that I follow in the flat earth movement. I've done a lot of study on this, and I've talked to some local people who believe in a flat earth, so I'm trying to understand where they come from. And, you know, of course, with my physics background, I have some different assumptions. And then here on the right, we have three other scientists who work for creation ministries. Some of them have been speakers here before too, like Rob Carter, Jason Lyle, and Danny Faulkner. So they are, and by the way, what I'm doing here, I've got way too many slides to show for this 1 hour that I have. But I've got all of my slides are on my website. If you look at that right here, my name and then /flat-earth. So all of which I talk about is on the website, plus a whole lot more. I've got all the evidence for what I'm speaking about on that particular web page. So the reason I got into it is because I find that there are more and more people starting to believe in a flat earth. So I'm trying to understand why they believe in a flat earth, what brought them to that. And so I put this program together. And so I wanted to understand, you know, the origin of this, and that's why I call this talk the flat Earth phenomena. So this first slide is normally the way I present topics. I'm going to tell you what I'm going to tell you. I'm going to tell you, and I'm going to tell you what I told you. So it makes it easier for you to understand. Okay, so I'm just going to flip right through. These are the 10 topics I'm going to go through. A bit of history of belief in flat earth, a bit of history of belief in spherical earth, and what do flat earthers believe, what does the Bible teach, and then the meat of the presentation is these three here. Number 6, 12 evidence that people say this shows that we live on a spherical earth. And then I look at the flat earth model and say these challenges, can the flat earth model answer those questions? And then I'll talk about it in the summary. Flat earthers have certain assumptions that they make. And those assumptions need to be true in order for the flat earth to be true. So keep that in mind as you go into this. So I'm just going to show you a few. It turns out as I study this, not all flat earthers believe the same thing. And so it was kind of hard to pin it all down. But anyway, people that are believers and believe that God created a flat earth go to these scriptures and say, look at these verses. You know, the earth is flat. The earth doesn't move. It rests on pillars, goes around the earth, lights in the dome over the earth. So these are just some verses, and there are hundreds of verses, which we'll look at a few of them. So they believe that the earth is flat, and that there is a dome over the flat earth. And here is the answers in Genesis. This is this rendition of what they believe. And this is what I use pretty well as a basis when I speak on flat earth issues. They believe that there's a flat earth with all the continents and the oceans we see here. But they believe that the sun and the moon are within a dome or a firmament. And that firmament is about 3,000 miles high above the flat earth. So within that, you have a very small sun and moon rotating around. Okay, so those two, And then there's stars, and then also there are planets you can see that the ancient could see as well. And so you might say, with a small sun, how do they cover, the Earth with the sun, or part of the Earth with the sun? Well, they've come up with the idea of a spotlight sun. So the spotlight sun is said to be 32 miles in diameter, and that is because it's a funnel. It only shines in a certain fraction of the Earth, and it goes, around this orbit within one day, and it covers the Earth that way. You can see it here. Of course, it doesn't move that fast, but it goes around in a day, and the moon doesn't go at the same rate as the sun. It is its own frequency. But that's the basic framework that we're working with. They've also come up with a map, which they call the standard map of the world. Gleason came up with that in 1892. And so that is just one way of mapping what we see on the Earth onto a map. You can't take a spherical Earth, either the map of a spherical Earth, and put it on flat paper, two-dimensional. Doesn't work. You got to make some assumption. So this is what they use here. So in summary, the concept of the Earth is a round stationary disk, like this here, 25,000 miles in diameter. The dome is about 3,000 miles up here. The sun-moon orbit around the northern axis. The North Pole is the northern axis, so the sun rotates around that. And so in the dome, you can see stars are in the dome, the 3,000 miles up or so. And you can also see 5 of our planets. And in fact, the ancient could see these 5 planets because they're very dim lights in the sky, and they identified these 5 planets. And then what is surprising, I guess, to spherical Earth people is that the Antarctic is not a continent. It is a wall around the flat Earth. Okay, so that's the platform we're dealing with, and we'll look at that from that perspective. First of all, I found it very interesting to look at the history of when did people start to believe in a spherical Earth, and also look at when people started to believe in a flat Earth. First, the spherical Earth. Around 570 BC, Pythagoras, he could see the sun and the moon and 5 planets in the spheres, with the Earth in the middle. And they had the moon, of course, is around the Earth, and the sun is also there, but then 5 other planets. Okay, but he mentioned that he thought that the Earth was a sphere, although he had nothing to base that on. And then another Greek astronomer came along and said the Earth rotates on its axis. So in other words, there is an axis going through the North Pole, and the Earth rotates around it. Another astronomer came up with in 300 BC that he made the first mention that we know of a heliocentric model. In other words, the Earth is not in the center, it's the sun that is in the center, and the planets are going around it. But that didn't go anywhere for hundreds of years. Okay, how did people measure things back in those days? They used trigonometry. Trigonometry was invented in this period as well, and they used a method called the parallax. And what it is you look at, determine the distance of the Earth to the moon. And of course, by this time, they were assuming a spherical Earth. So if you go to a place on Earth here, and you go 90 degree up is the zenith of A, and you can measure the angle to the moon from 2 different places, and using trig, you can come up with a pretty good estimate of how far the moon is away. So it's around 240,000 miles. I forget exactly what he estimated, but it was very close to that. And you can use the same method to measure the distance to stars, although in that day you couldn't do much of this at all until telescope was invented, you had to do what you could with less. Okay, then there's the...
We're going to need to change your microphone for some reason.
Okay.
Excuse me.
I'll just take this off. Let me get untangled here. Okay, hey, people can hear that okay? I hope it's a little clear. Anyway, here's an astronomer, Greek astronomer in the 276 to 190 BC, Eratosthenes. He was a Greek astronomer, he knew math, and he was the first person to try to estimate how big is the circumference of the Earth. How could he do that? It's very, very difficult in his day. I'll show you another slide. And then there are other ones like Hipparchus, who also, he's the one that founded the science of the math of trigonometry, and he developed a method to predict solar eclipses. So here's Eratosthenes. Here's how he measured or estimated the circumference of the Earth. He was a Greek philosopher, astronomer. There was a well in Syene, which is today's Aswan, and he could see at noon, when the sun was directly above, that the sun shone right to the bottom, so he knew it was totally vertical to the Earth. And then he went to another place called Alexandria, and also with the sun at noon, he could see that there was a shadow. And the shadow was at about 7.2 degrees. And that 7.2 degrees is 1/50th of the circumference of the Earth that we know today. So he multiplied the distance between Alexandria and Cyrene times the factor of 50, and that came out 240,000 something. So that's how he did it. And again, it's using parallax. So a real accomplishment. Now, it wasn't exact, but with the instruments he had, that's what he did. So then comes Ptolemy. I'm sure you've heard of him. He's the one that came up with the geocentric model, and with the Earth at the center, and of course the moon rotating, orbiting the Earth. But then there's the sun away, and then there's 5 other planets that were moving around the Earth, or so it appeared. And he wrote a lot on the science there. We identified these here other planets, even Jupiter and Saturn, which are gaseous, and Mercury and Mars, which are rock planets. They could be seen without a telescope. And so when the telescope was invented, of course, they could see a lot more. And then we come to the 1500s, because the geocentric model held its place all the way up to this time until Copernicus came along. And he said, no, the sun is really at the center, not all these other planets, not the Earth. But again, it's a way of looking at it. The sun is at the center, not the Earth. Stars do not move with respect to each other. And he wrote a book on this too. And then we come to Galileo a little later. And there was another person, I believe it was in the Netherlands or Belgium, that invented the telescope in 1608. And so Galileo came up with a way to make a better telescope, and he was able to observe stars and rings and craters on the moon even, and sunspots. So he did a lot with it. And then comes Kepler, and he's the one that came up with his 3 laws of planetary motion. Remember, the Greeks thought a circle is what is perfect. But Kepler came across determined that the orbits of the planets weren't really circular, weren't complete circles, they were ellipses. So now let's look at flat Earth history. Flat Earth was believed by some ancient cultures, but not taught by early church fathers. There were maybe 1 or 2 that thought so, but not very many. And that was true until about 1838. Samuel Robotham came forward in the UK, and he was convinced that the Earth was flat based on looking at this Bedford level experiment. And he was looking at a canal of 6 miles long with a bridge at each end, and said it's flat, so the Earth is flat. And he published some work on that. Others joined in, and then we come to the 1800s. More people joined. The late 1800s joined that, and even in the 1900s, people wrote books on this. But then the interest dropped off, and then in the 21st century, actually, Eric Dubé is the one that really took off with this. He was the author of 2 books, 200 proofs that the Earth is not a spinning ball, and also the flat Earth conspiracy. So he wrote those 2 books, and they have gotten a lot of, and they've got a lot of response. A lot of people read it, and there's a lot of stuff on the net. So first of all, let me say, what is the bed level experiment? This was run by this guy in 1838. The objective was to deny that the Earth is curved. He used a telescope held about 8 inches above the surface of the water, and he had a boat with a flag on it, and that went from one bridge at one end of that canal to the other end, 6 miles away, and he said, I could still see that flag from where I was. And so he said, the Earth is flat. And that stood for a while until 1870, somebody came along and challenged anybody who could prove that the Earth was a curvature, and that's where Alfred Wallace comes in. But before I do that, I've got to explain a little bit about refraction. You know, light travels through the air, light travels through water, but when it goes from one medium to another, it could bend because the index of refraction increases going into water, and the index of refraction can be very high in some very solid materials as well. So atmospheric refraction is the deviation of light or other magnetic waves from a straight line as it passes through the atmosphere due to the variation in air density as a function of height. Even going from a high part of the atmosphere to the Earth, there's still a change in the density of the air, and you could see some refraction as well. So this refraction is due to the velocity of air through air decreasing with increased density. The denser the material is, the slower the light goes. So the density of the air decreases with height above the Earth. Light rays travel near horizontally. If they're going horizontally, they can bend. If they're close to the water, they are affected by the refraction and can follow that curve, actually. And that's where this person comes in, Alfred Wallace. Somebody challenged him to prove that the Earth was curved. Now, it turns out he was a land surveyor, so he knew something about this. And so Wallace did the experiment on the same canal that Robotham did, but he observed it with a telescope from one bridge 6 miles away to the other, just like Botham did. But he he used 3 poles of equal height and placed them one at the beginning, at the telescope where he stood, and one at the 6 miles away, and the one in the middle of the water. All of them the same height above the earth. And so he said, if there is no curvature, my telescope, which is, 13 feet up to avoid any atmospheric refraction interference. So there wasn't much refraction to deal with there. So 3 equal poles. If there was no curvature, he could see the straight. But he noted that the middle pole, he could see partway down of that. In other words, the B and the A. Whereas if it was flat, it would have been like that. So this proved that the Earth was curved. But he got a lot of pushback from that. Another person in 1901 did the same experiment, showed the same curvature, but that didn't get a lot of publicity. But nevertheless, most people still believed in a circular Earth. Today we have major flat Earth proponents, and I'll just mention Eric Dubé because he's one of the biggest influencers. Note that he's not a believer. Mark Sargent, who I believe is from Whidbey Island area here, and then Flat Earth Dave, who does a lot of videos on the Flat Earth movement. And then, surprisingly, at the bottom here, we have Michael Heiser, who was a compromising theologian. He believed that the Old Testament taught flat Earth, but he got it wrong. But nevertheless, he has also been very influential with believers in convincing them that the Earth is flat. And then another one, which is probably today more prominent, is Pastor Dean Odell in Alabama. Okay, so these are the major proponents today. What do flat earthers say? Gravity makes no sense. It's buoyancy and density. In other words, if something is heavy, it will go down. In other words, if it's heavier than water, for example, and more dense than water, it will go down. And so it's the buoyancy and density that do what we say gravity does. So water doesn't curve. This is what they say. And water finds its own level. They asked the question, if the Earth really is spherical, it is actually moving at the equator at about 1,000 miles per hour, because you've got to get around the whole Earth in 24,000 miles. So it's about 1,000 miles per hour. Said, how could water possibly stick to a spinning ball? But we believe that's gravity. They say, well, water can't flow up. Well, there are some rivers that run from south to north, and if the Earth is spherical, how can the water go up? And of course, the common ones that they say, well, look at there's a boat over here in the lake or the ocean, and I shouldn't be able to see it if the Earth is curved, but I do see it. Therefore, the Earth must be flat. It's a little bit more complicated than that, but that's... So anyway, that's basically what they say. Here's the book I mentioned. You can get this book, 200 Proofs. It's right on the web. You can just search for it. You can download it. I've downloaded it. I've looked at some of their arguments to see what they say. Okay, now let's go to what does the Bible teach? And they will say, flat earthers will say, there are 200 or more verses that imply that the earth is flat. Many of these verses, as we'll look at them, are dealing with other issues different from whether the earth is flat or spherical, or even geocentric or heliocentric, because the Bible doesn't address that at all. But if you look at the context of those verses, you'll see some of them use different genres. They could be historical, history, accurately covering history, or they could be poetic or allegorical. The meaning depends on the context, grammar, or could be literary. Many of these so-called flat earth verses are from poetic books, and some talk about the land and not the planet. They use equivocal or idiomatic language. They cherry-pick verses not found in all translations, and they would say flat earth. Well, look at people in history. Pastor did teach flat earth. Well, there were a few, but not very many. So our colleagues from Creation Ministries International, we've had them both as speakers, Dr. Carter and Dr. Sarfati. They did a detailed review of those 200 plus verses, and they classified them into these classes. Verses that have nothing to do with flat earth argument. In classical terms, these are called non sequitur, or doesn't follow. The verse that does nothing to do with the shape of the earth. Second, verses that are ambiguous in relation to the shape of the earth. They use equivocal language, so it's hard to determine what was meant by the author. A proper analysis would require decent knowledge of ancient languages or context, or at least a careful reading of scholarly sources that discuss the passage in question. And third, there are a few verses that involve a misreading of non-modern German or English terminology in some older versions, often cherry-picked verses. Okay, these two scientists looked at these verses very carefully. And then another scientist I read is Danny Faulkner from Answers in Genesis. There are 4 phrases which are misleading and easy to say, well, those definitely prove that the earth is flat. And there's phrases like 4 corners of the earth. And there's both in the Old Testament and in the New Testament. What do they mean by that? And we say that's idiomatic, that's not literal, they're not standing literally. And of course that doesn't agree with the flat earth model anyway, because the flat earth model is a disk. So 4 corners, I'm not sure where they would be. So that's how that is looked at. Then the other phrase is ends of the earth. And that phrase appears in the Old Testament, actually Old and New, 28 times. And just looking at these 3 here, in Psalm 67:7, may God bless us still, so that all the ends of the earth will fear him. And here, all the ends of the earth have seen the salvation of our God, and turn to me and be saved, all the ends of the earth. So that's not pointing to some geology, that's pointing to people. Okay, so it's idiomatic, and you can't make anything about the shape of the earth from that. And then the harder one is pillars. In Job 9:6, he shakes the earth out of its place, and its pillars tremble. When the earth totters and all its inhabitants, it is I who keep steady its pillars. And the Lord reigns. He is clothed with majesty. The Lord has clothed and girded himself with strength. Indeed, the world is firmly established. It will not be moved. So again, if you take that literally, what does that mean, that the earth will not be moved? Certainly it's not moving necessarily relative to us. If we are the object, I don't see the earth moving relative to me. But, so how do you interpret that? And then probably the hardest one is the one that deals with the firmament and the dome. It goes all the way back to 1 Genesis 6:8. It talks about the dome over the earth in a flat earth model. The dome is the firmament. I showed you that dome that's 3,000 miles above the earth. They interpret that from Genesis 1, verses 6-8. So that's based on the Hebrew word rakia, but actually the verb rakwa means to spread out. It doesn't talk about dome or firmament. So in most English translations today, treat it as the expanding, the expanse, the sky, for example, like they do here. So it's a noun versus a verb discussion there. But anyway, there is, if people don't want to follow that, go to the Answers in Genesis website. On Following Flat Earth, it's written by Danny Faulkner. And all of these links in here, if you download my slides, you can just click on it. It'll go right there to that web page. There are also some verses that talk about, or seem to talk about a sphere. And there are about 100 verses, people would say. And so in in Isaiah 40, verse 22, it is he who sits above the circle of the earth. and its inhabitants are like grasshoppers, who stretches out the heavens. So that's getting back to, the expanse. And then Job 26:7, he stretches out the north over the void and hangs the earth on nothing. So, it can't be sitting on pillars, it's hanging on nothing. Job 26, again, the circle on the face of the waters. And when he established the heavens, I was there when you do a circle on the face of the deep. Again, go here and you can look at that. So now I want to get into the meat of my presentation, and that is, I'm going to look at 12 what I call evidence, probably the earth is a sphere. And so I'm going to quickly run through this list, just keep note of it, because I'm going to discuss each one in detail, but these are the ones I'm going to go through. Okay, so those, and the first two are ones that the ancients really picked up. First of all, the disappearing over the horizon. You've all seen boats on water, on lakes or oceans. When they're close to shore, they're large, and then when they move away, they reduce in size. Okay, and that seems to indicate there's a curve there that you can't see beyond. And then here's some other ones here, more extremes. And here, this one here, I know you can't see very clearly, but there's the observer standing here in one place on the earth, and he's trying to look over the horizon. In other words, the horizon is this point. That's as far as he can see, because after that, everything goes down. So you can't see over the horizon. And so we often refer to how far is the horizon away. And this picture, this triangle explains this. So we have the H here, we have the observer, we have the horizon here, and we have the earth as let's say roughly 4,000 miles in radius. And so you know how far H is away, and if the observer is standing above the earth, maybe a few feet or 20 feet, or doesn't matter, that's a H, okay? So there's H plus R. And then the other part of the triangle is the D, and that's the distance to the horizon that the observer can see. Beyond the horizon, if there's no refraction, he could not see beyond that down here. Okay, so remember the Pythagorean theorem? A squared plus B squared is equal to C squared? Well, here it is. R squared plus D squared, R squared plus D squared equals R plus H squared. Okay, now since this H, we were talking just about feet here, is very small. So you can in fact say this H, it falls out of the equation. But if you measure, if you work the equation, square this out, the R squared falls out, and it comes down to H. This distance here that the observer is standing is D squared over 2R. And so if you're 1 mile away from the horizon, you're only 8 inches, is where the horizon happens. And you look at 6 miles, and you have 24 feet. So if you have, like the Bedford experiment, 6 miles of canal, that's 24 feet down that you can't see if the earth is curved. You can see part of it as the flags go down, but you see less and less. And so these are examples of disappearing over the horizon. And refraction allows one to see further than one would expect. And that's what happened in the first experiment in 1838. Bending light around the curve, especially if you're observing very close to the water, because then the light is going to follow. So here's an example. People was standing on the shores in New York, Lake Ontario here. There's a CNN tower, which is 1,800 feet tall, okay? And so there are high rises here. So it turns out you can't see the bottom of that because it's a curve, and you can calculate that. Okay, so this is approximately, this is where the bottom of the tower should be, and so that's 600 feet below sea level. So you can see part of the tower, but the farther away you go, you're going to see less and less, and that's consistent with the curvature of the Earth. And this is another thing that people need to realize. The strength of the refraction is not constant. It all depends on weather conditions and differences in temperature. So with low refraction, if there's no refraction, you could see the whole building is not visible if it's over the horizon. If there's medium refraction, you could see some of the tower you're looking at here. So you see some. If it's very high refraction, well, there's a chance if you're close to the water that you could see almost all of it. So that's how refraction works. And of course, there's a limit. I mean, you can't see thousands of miles. Okay, so number 2, on what shows a curved Earth. The ancient figured this out. When there was a lunar eclipse, there was a shadow of the Earth on the moon. You could see that up in the sky. And so you'll notice the curves here. It's very slight because the Earth is greater in size than the moon, but still there's a shadow. And you can see over time the shadow moves as well during the time of the lunar eclipse. So that's a pretty easy one to understand. The ancients knew that. They used that to determine there was a curve in the Earth, all the way back to 4th century BC. And then with the solar eclipse, of course, then we have the moon in between the sun and the Earth. And of course, these are not to scale. But anyway, this is what causes a solar eclipse. And I'm going to show you later on some more details on that. So in fact, the astronomers, they know exactly when the eclipse is going to occur because they know the movement of these bodies throughout the atmosphere, throughout the space here. And so that's why on April 8th of this year, you had an eclipse go through, solar eclipse go through the U.S. Third, it appears, you're looking in the sky, that these planets and the sun and moon are spheres. And for the Earth, for the moon, it's easier to determine because you're looking at different angles of the moon from different places. And so it always looks like a sphere. If it was a disk, you'd see it, if you're over here, you'd see it different than, if you're over there. So if it always looks like a circle, it probably is a circle or a sphere. And so here, all these look like spheres. So why isn't the Earth also a sphere? Then the other thing you have from the ancients is you have the classical planets moving across the skies. I mean, the stars you can see, they say many of them fixed stars, but you have the 5 planets, that you can see moving in the sky. The ancient could see them very dimly, but they could still see them. These were referred to by the Greeks as the wanderers. And but you see all the many more stars back there, and they're called the classical planets. And after the invention of the telescope, of course, we could see a whole lot more. The 5th one is the fact that people realized in the old days, you didn't travel from one area of the world to another very much. Pony Express, couldn't go very fast. But when you start using trains, people start realizing that, hey, the sun rises at a different time in this part of the world than it does in that part. And so there must be something that's moving here. And so there's an astronomer that lived in the 13th century, John Sacrobosco. He said that the Earth too is round is shown thus. The signs and stars do not rise and set the same for all men everywhere, but rise and set sooner for those in the east than for those in the west. And of this there is no other cause than the bulge of the Earth. So he had figured it out there as well. if you go up high enough, high weather balloons or other balloons, you can see images of a slight curvature of the Earth. And then, of course, when you got the Earth and Moon, the Apollo astronauts, so of course, one of the arguments, well, they didn't really land on the Moon, but we're putting that aside. Here are pictures of the Earth taken from the Moon with the Earth lander. So it's possible to see pictures. And here's, some of you may have heard, the International Space Station. It's in the news these days because they have 7 or 14 people on that station. Remember, they sent up 2 astronauts recently, and they're trying to figure out how to get down from there because they had some mechanical problems. So this huge satellite, a space station, is going around the world. It's 250 miles above the Earth, and you need a space shuttle to get people between that and the Earth. Snapshot from the International Space Station. This is the astronaut who took that picture. You can see it's quite obvious that there's a curve, and here's an astronaut outside of that space station. And the Hubble Space Telescope, again, 335 miles above the Earth. And then the latest one is the James Webb Space Station. And that is 1,000,000 miles above the Earth. You can see here with the sun, the Earth, and the Moon orbiting around the Earth, and then 1,000,000 miles out is the Webb. And it has an orbit that is different from the Earth orbit. Okay, so, and this is one of those pictures that were taken from there. Now we come to number 9. I'm sure some of you, many of you hopefully have heard of the Foucault pendulum. You see that in different museums. It's a weight, a ball usually, at the end of about 200 feet length of something that holds it there. And you start it swinging, in one direction, and then over time, it starts swinging a different direction. Why is that? Because the Earth is rotating. Okay, you can see it here. This steel ball here, starts out here, and then eventually, moves further and further in one direction. And so 24 hours, you're going to see it swing all the way back again. So that clearly indicates that the Earth is revolving. And the other one that shows the Earth is revolving is the Coriolis effect. And this is a force that acts on object in motion within a frame of reference that rotates with respect to an inertial frame. And this is where you have a difference in action in the northern hemisphere versus the southern hemisphere. In the northern hemisphere, if you're far enough away from the equator, you can have water that you have in a washer or something, or some holder, and the water rotates to counterclockwise. So that's in the northern hemisphere. But if you're in the southern hemisphere, it goes in the other direction. Anybody been to Australia or the southern hemisphere where you can see that? But I mean, that's pretty well known these days. And you can see something starts out one direction, but because of the movement, the rotation, it changes direction. And in the northern hemisphere, it's different than the southern hemisphere. And it's also true of storms, it turns out. In the northern hemisphere, we have typhoons, not here, but in other places in the world. And there, again, they go counterclockwise. And in the south, it goes clockwise. Why is that? Again, it's the rotation of the Earth, the force there. So there's a bunch of pictures that explain that, but okay, I want to move on to another one here. First of all, I have to define some terms here, because some of these you may not have heard about. This is pictorial, showing the Earth here. Got the equator, you got the North Pole here, got the South Pole there, and then above the North Pole, there's a star called the Polaris. Here, the Polaris star. You can, in the northern hemisphere, you can see that in the sky, above the North Pole. But on the other part, further towards the equator, you'd have to look at it at an angle. So there's the Polaris there. So here, the North Celestial Pole is the point in the sky above the North Pole. That's a very bright star that you can see at night, which is called Polaris, North Star. In the south, there is also a star, but it's not near a bright star, and that is the Southern Cross. I don't know if you ever heard of that in the southern hemisphere. So, but the point is, these stars can only be seen from certain places on Earth. I mean, if you're down in the south, way down in the south, you cannot see the Polaris star, over the North Pole. You just can't, because it's, the curvature of the Earth. If the Earth was flat, you should be able to see all the stars that people can see, because it's flat. And with a telescope, you can aim it at any place you want, and you can see them. But in the south, you're limited to what you can see, and in the north, you're limited to different stars that you see. And the second thing about those stars is, again, in the northern hemisphere, the stars revolve anti-clockwise, counterclockwise, around the Polaris, or more precisely around the celestial North Pole. And in the southern hemisphere, they appear to revolve clockwise. So it's the same thing as the Coriolis effect, because of the rotation of the Earth. And you're a different hemisphere, it's different. If the Earth was flat, they'd all be moving in the same direction all the time. Okay, so those are the 12 for the evidence that shows that Earth is probably a sphere. Now we look at challenges for the flat Earth model. So I'm going to look at these 12 things here as well. Okay, the first one, they don't believe in the law of gravity is taking the effect that we see. They don't believe in Newton's 3 laws of motion, Kepler's 3 laws of planetary motion, and et cetera. Here, this table here shows the index of refraction I was talking about. For the vacuum, for not much in the air, it's 1.000. There's no refraction. For air, it is 1.000277, not very large. But then in water, it's 1.33. Ice, 1.31, and so on. So different material, different fractions. Laws of physics. Remember, Newton came up with 3 laws of physics. Newton's laws of motion, and then Kepler's laws of planetary motion. And I won't go through them, but if you have an interest, you can download my slides and read all the details there. But the other thing I want to point out, you well know the gravity, the law of gravity. The force equal the gravitational constant times the mass 1 times mass 2 divided by r squared. It's over r squared. So you can measure that. That's a challenge for flat earthers if they don't believe in gravity. And one interesting thing, well, I'm going to point out the next one, here. Tides. What causes the tides? The moon. The sun also causes tides, but it's a weaker effect. But the moon is much closer, so the gravity causes those tides. You may have heard of the Bay of Fundy. That's one of the largest tides, 40 feet or so. And different places, different height of tides. But it's the pull of the moon. The other thing is that the moon also has an effect on the Earth because it's close to the equator. It actually makes a bulge in the Earth, so that the Earth is the diameter at the equator is more than the diameter at the poles, from North Pole to South Pole. So if you think about the law of gravity, that means that you weigh more at the North Pole than you do on the equator. Somebody want to test it out? But it's true. You can work it through this here law of gravity. Okay, and that showed it there. But you know what tides are all about. Here's another one that I'm very familiar with because I used to fly a lot. So going from Los Angeles to Boston nonstop takes you 5 hours and 35 minutes. Going reverse from Boston back to Los Angeles takes 6 hours and 20 minutes. Why is that? Because the Earth is rotating and there's wind circuits up there. So something is moving. Is a flat Earth, you wouldn't expect that. Another one here, that with a telescope, people were able to observe that these 6 planets that we know about they all have their own orbit. They orbit at different rates and they're never all in one line. But here is a case on June the 3rd this year where they seem to be very close to all in one line. Why would that be? If it's a flat Earth, of course you couldn't have that. Okay, now another comparison between the spherical Earth and the flat Earth. The Earth in the spherical model, 8,000 miles diameter, 25,000 miles circumference. These are rough numbers, but close. Moon has a diameter of 2160. Sun is 400 times the size of the moon. Sun is 109 times the size of the Earth. Sun is 93 million miles away. Moon is 239,000 from the Earth. And stars are outside of the solar system. If you got a flat Earth concept, you got the Earth as a round disk, 25,000 miles across. The dome is 3,000 miles above it. And the sun and the moon inside are 32 miles in diameter. Sun and moon rotate above the Earth, but under the dome. Stars and the 5 visible planets are also in the dome. So what does that mean? How do you interpret the fact in the flat Earth model, you have a spotlight sun issue. If the spotlight sun is this, it's just bringing light to one part of the Earth. And yet, if you go from here, the sun is this far away. If you're down here, it's only 3,000 miles up. But at some point, with a very low angle here, that sun, if it's 6 times further away, not 6 times, but the square root of 6, it is, if it's twice as far away, it's going to look like a quarter in size. Okay, and if it's further than that, it could be as much as 6.4 times bigger or smaller. But do we observe that? No. We observe a moon, moon and sun they always seem to be pretty equal in size. So that's hard to explain. In the flat Earth model, you also have the issue, how does the sun set? How does the sun rise in a flat Earth model? Because, you have to make it look like that using the spotlight sun. So then you have these kinds of issues, with the sun going around, and forget the moon, that's going at a different frequency. The moon, sun, moon rotate in the sky without gravity. If gravity is, what holds the sun and moon up? Okay, and what causes it to move between the different seasons? The sunrise, sunset should never be below the horizon. Can never be below the horizon. How do you explain a lunar eclipse? How does the Earth get between the sun and the moon? They're both rotating here. How does the Earth get between? It can't. You cannot explain a lunar eclipse. Okay. You can't illuminate the whole ice wall around this whole Earth at once. You can't explain 4 seasons, and this is where solstices come in. So just to remind you, with the sun, the Earth orbits around the sun, and it goes through 4 seasons. But remember, the Earth has a 23.5 degree tilt to it. And therefore the sun hits different parts of the earth more at certain places than others. So you go through the spring equinox to the summer solstice here, and see during the summer solstice, the sun is also shining on the North Pole, and then through the autumn, and then through the winter. These may show a little bit better here. So the sun here, you got the June solstice, the summer, and the sun is up in the Tropic of Cancer. And see, the sun goes from the Tropic of Cancer to the equator here, and then up to the Tropic of, go down to the Tropic of Capricorn. So the sun moves or hits different parts of the earth at different places. That's how we get our seasons. And this is another way to look at showing the different seasons. There's the, okay, and here, sun solstice and the winter December solstice. You can see the sun hits the top. You get days of sunlight only, no dark days. And in the Antarctic region, the circle there, you also get light during the summer solstice. Okay, so it's different in different seasons, and you can't duplicate that in the flat Earth model. It just doesn't. Okay, solstice predictions for the flat Earth. We have the North Pole in the center, right here. We have the Tropic of Capricorn, which is closer to the Arctic. Sun circles above the Earth around the axis, radial distance from the North Pole to the Sun. It's closer here when the Sun is going here, and then there it's the furthest away. So again, it travels different distance. The Earth is stationary, but the Sun has to travel faster to get around the same, around there once. How does that work? How does it change speed? So anyway, here's the number 8 here, flat Earth eclipse. I talked about the lunar eclipse. You cannot explain that for flat Earth model. If you look at Eric Dubé's explanation, he can't explain it. Same thing with the solar eclipse. Remember this solar eclipse in April? It came across this path exactly as predicted, because we know the movements of all these bodies in the universe. And so it followed this path. And in 2017, there was another one, but it followed a different path. Could we predict that? Yes, we can predict it exactly, within seconds of where it's going to be. You cannot do that with a flat Earth model. So then we come to satellites. There are satellites in the sky all over the place. I'm running out of time. I'm going to go quicker here. So I'm not going to go through all of these, but there are different satellites at different heights. One thing to note is GPS satellites, navigation satellites, up at 12,000 miles above the Earth, orbiting. And all these different kinds of orbits. The low Earth orbit, the medium Earth, and so on. But the one I want to point to is the global GPS that you use to navigate. How you were able to do that? Well, you've got 24 satellites in the atmosphere at 12,000 miles above the Earth, and most of your smartphone will see 4 of those, and it can use those 4 to determine exactly where you are. It needs that information. But the other thing that you have to recognize, the signal travels from the satellite to your phone. That takes time. So these GPS satellites, as observed by those in the Earth, they run 38 microseconds faster per day than those on the Earth. There's that much difference. So if you let that accumulate, you'll be way off. And okay, so that's where corrections have to come in there. Same thing with land surveying. You have to make a correction. If you look at the literature, I've got 3 examples here. You have to make corrections for Earth curvature and refraction, all 3 of them. And then finally in battles, I mean, if you're in the ocean and you've got an enemy that is 30, 40 miles away, you know, how do you shoot a gun at him? How do you aim a gun at him? You have to account for the curvature of the earth. The curvature, you have to account for the rotation of the earth, the force of gravity, all of these things, you know, air resistance and refraction, all these things have to be taken into consideration. And there are tables that are maintained that they use. You know, the U.S. Navy has tables for that. Okay, finally, number 12, the Antarctica, I would say, can't be an ice wall. It is, in fact, if you look at the map from the spherical Earth point of view, this continent is the 5th largest continent on the planet, the 5th largest. But the flat earther would say, of course, that's all distributed, you know, around the large disk of Earth. But you have to realize, see, this map has different places, different camps and stations on here. They're exactly different latitude and longitudes. And this whole Antarctic continent was claims were made by different countries. So they claim a shape of the pie. So here, for example, Australian claim. So that pie is this section here. How do you map that to a flat Earth? And same thing here, the New Zealand claim. There's a Norwegian claim. And so these 7 have claims, but then there are other stations which are owned by different countries as well. So that's what the map looks like on the spherical Earth. How do you map that to the, you know, the ice wall? Here's a picture of Antarctica taken from Galileo space. So there are challenges left for the flat earthers in astronomy. We covered most of these. Lunar solar eclipse, you cannot predict on a flat Earth model. The planet alignment, that can't happen in a flat Earth. Stars rotating around the celestial poles, different on the south hemisphere and the northern hemisphere. Flat Earth dome with the sun and moon inside. Solstice predictions, you can't do that on the flat Earth. And dealing with satellites, of course, is a big deal. Global positioning with satellites above the dome. I mean, they're 12,500 feet above the Earth, so they're above that 3,000 miles there, and low Earth orbit satellites. So then, if you look at how do flat earthers come to their conclusion, they have to make assumptions. And here's the 12 assumptions that I think they have to make. Gravity is not real law of nature we need to deal with. Things fall down because of density and buoyancy. The Earth is stationary. It's not moving in space, and it's also not rotating. Space does not exist beyond the dome. Nothing can orbit the Earth, you know, because it can't go outside the dome. Newton's 3 laws of motion are fake. Kepler's 3 laws of planetary motion are fake. No satellites or space stations, that's their assumption. You know, GPS satellites don't exist. They're done some other way, they would say. Astronauts have not been to the moon. NASA lied about everything they claimed. NASA photos are in space are fake. They're photoshopped. And number 12, Antarctica is an ice wall around the Earth disk. And we've just shown that it's not possible to do that. So then in conclusion, this is what I told you, if you remember. Some ancient cultures did believe in a flat Earth. The Bible text does not require a flat Earth. Observations from the 5th century BC by Greek astronomers to the 19th century AD have shown Earth to be a rotating sphere. An incomplete experiment by Robotham in 1838 renewed an interest in a flat Earth, but didn't prove that the Earth was flat because of what Mr. Wallace did. He showed that was not a good test. Scientific observations show the Earth to be a sphere, those 12 I showed you. The 12 flat Earth models, the model fails to explain the observations we see. why are so many people interested in the flat earth? We believe it's social media. It's all over the social media. And there are flat earth societies, and there are people that have oodles of video clips would try to convince you the earth is flat. So, and the assumptions made by the flat earthers, the 12 that I mentioned in the previous slide, they cannot be verified. They have to be verified for flat earth to be true. And I would challenge flat earth people, show me which of those assumptions are true. And I would say none of them are true. And then what problems, those 12 problems with the flat earth description, it doesn't work in my mind. And then the 12 ways we showed we could observe that the earth is a sphere, you have to show me that I was wrong in some of them. So, and the spherical earth is supported by the Bible and by science. The Bible doesn't really come out and say, unfortunately, because they didn't need to do that in those days, but it is consistent with what we observe, is consistent with what the Bible says. So that's it. So all of my talks can be found on my website here, messages you can poke around. But if you want this here, go to my website at Flat Earth, and you can download my slides from there. You can, and also last night I recorded this talk, and so there's another recording on there. It's 1.5 hours long, and so last night I said I need to cut this back. I need to cut some things out because people don't want to listen to an 1.5 hour lecture. But if you do want to listen to an 1.5 hour lecture, it's on my website at this webpage. So thank you for your attention, and we'll take some questions if you have any. And just to let you know, I have been communicating with some people that believe in a flat Earth, and I've ended up sending them these slides as well. But it's hard to convince. We're not talking the same language. I feel sometimes. But anyway, even if you're flat Earther out here, you believe in a flat Earth, I'll be happy to talk to you as well. I challenge you to show my 36 points, which ones are not true, and I'll look at them.
That canal that's 6 miles long, what's the name of it? Is it still around? I mean,
you're talking about the experiment, the
yes.
Bedford. Yeah, put your microphone.
What is that canal?
Yeah, that was a canal.
Where is
with
it?
Very stable water. No ripples in it.
So I know, but where is it? Is it
in England?
in England? So how could that? Because when in the atmosphere, when you set up, from a satellite or whatever, we see the curvature of the Earth, right? So in that 6 miles, and you have those 3 points. What kind of a measurement is that you'd see the curvature in only a 6 mile span?
The poles were exactly the same length, I think 12 feet or so high, maybe a little higher. And he looked at from the first pole and the one in the middle, he could see partway down the pole. If it was flat, he should just see the top of the pole. Yeah.
6 miles.
Yeah, in 6 miles, that one was the same height, because see the third one is right in the middle of that.
But you're not going to have a drastic measurement. It'd be so minute in 6 miles.
Yeah.
Right?
Yeah. And other people are going to run those experiments too, and they have. Bill?
Well, I lived in Africa for over 20 years at about 14 degrees south of the equator, and I saw the Southern Cross many, many nights, and we could sometimes see the Big Dipper, but it would be upside down. where we could see it.
Yeah.
But anyhow,
What country were you in again?
in Zambia,
Yeah. Yeah. So you could see it down there in the southern hemisphere, but if you're up here, you could not see that.
no, not really. But the Southern Cross is beautiful. I saw it many, many nights.
The movement, the flat earth movement, the flat earthers themselves. The flat earthers themselves, the group, the people, the individuals who make up the flat earthers. Is that a movement that is mostly social media based, or do they have missionaries? Do they have evangelists? Do they have seminars? Do they have forums that they attend and produce literature and disperse?
I didn't catch what you're.
The flat earth movement, like Christians, do they evangelize? Do they have missionaries? Do they evangelize? Do they have missionaries, the flat earthers? Yeah. Uh-huh. Right. Okay. Are they aggressively anti-Christian or anti-religion like a neo-atheist? The ice wall, that's the first time I've ever heard of that. Is that what keeps the waters inside? Okay, okay. Okay. Has anyone ever, and I'll give the microphone back to this gentleman, has anyone ever posited the question, just in humor, are there edge tours? Yeah.
Oh. I'll do it after the meeting. Yeah, we'll talk after the meeting. Okay. So are there other? Yeah.
Just out of curiosity, in any discussions you have with flat earthers, what do they say is on the bottom of the disc? Like,
What's at the bottom of the desk?
what's under, what's on the bottom?
Yeah. That is question is what's what's below the disc? Right, and they have drilled holes. People have drilled holes in the earth. And they've gone like 10 miles or more, some of them, and they will say, but that's as far as it goes. But you have to ask others how they, yeah. Well.
Question and an answer. How about volcanoes? We know that something erupts from volcanoes, so it all comes to the, our knowledge that there's the nucleus of the Earth. We know that it's spherical. There's something inside. There's the minerals. There's this and that. So that proves when a volcano erupts, right?
Yeah.
We proved it.
Well, okay, I think we can bring this to an end, and thanks for your questions. And let me just wrap it up with a few notes here. Let's see. Rick, if you could bring up the last slide there. Yeah. So just to remind you that Mike Riddle will be here next month, Wednesday, and we'll have a meeting on the 27th of September with Mike Riddle here. But then also remember that he's doing that one-day class, Apologetics for the 21st Century, where he's discussing a lot of the cultural issues of the day. And there are flyers back there you can pick up and get the details on that. So again, Mike Riddle is well known to this audience. He's got a company called Training Initiative, and he's been doing this for years. And he's spoken on creation versus evolution and cultural issues for a long time. So he's well versed in all these topics that he's going to discuss in September. So just to remind you, there are flyers on the table on the back. If you're not on our mailing list and you want to add your name, there's a sign-up sheet on the back there as well. And there are some refreshments in the kitchen area there. And of course, we have books and resources and DVDs and the tables there that you might want to take a look at as well. And remind you, the way we support this ministry is through donations, and you can do that in the boxes there. So let me close up in a word of prayer, and we'll be dismissed. Father, we come to you this evening just to thank you for this time. Thank you for the opportunity to share this information with the folks here, and we pray that each one would have learned something new and be able to share that with those in their